Hello, welcome back. Today we will quickly summarize for you the oxygen transport. Okay, you have seen this oxygen transport before, but in different places. Let us put it in one basket and try to make things easier for you for exam purpose. Okay, you have seen oxygen transport happening in case of hemoglobin, where we have a heme iron center. You have seen it is happening in hemerythrin, where you have two non-heme iron centers, and of course you have seen in hemocyanin, where you have two copper centers present. Let us try to put it in one place and see their differences. We will also see a very little example or some selected examples of the synthetic model system that exists to mimic these oxygen transport enzyme. Hemoglobin and myoglobin is first up. So, in myoglobin you have seen there is a porphyrin center and there is an axial site which is bound with the porphyrin site, porphyrin iron center, and at the distal center oxygen binding is happening, right. This is one heme center. In case of hemoglobin there is 4 such heme centers present. There is a allosteric effect, or one oxygen binding is affecting the oxygen coordination of the others. Okay. You have seen the sigmoidal curve for the oxygen binding into the heme centers. So, that is all fine. Hemoglobin versus myoglobin difference is, it is 4 iron center in case of hemoglobin and 1 iron center in case of myoglobin, that is fine. You have seen a tabulated format of which differentiate hemoglobin and myoglobin in the previous class. Okay. Now, binding of oxygen to protoporphyrin 9, we have seen it is also quite exciting. You have seen the spin change from high spin compound to low spin compound you are forming. You have a ferrous, means iron 2 plus oxidation state, and you have ferric, that means iron 3 plus oxidation state. Upon oxygen binding, this porphyrin iron species goes to iron 3 plus superoxo intermediate, which is then forming the low spin ferric compound, right. So, this is iron 2 plus, it is outside the plane, it is not really inside the plane, high spin ferrous, okay, and this is the histidine binding. Remember, for cytochrome P450, where oxygen activation is coupled with substrate activation as well as substrate oxygenation chemistry is happening, there it was a cysteine ligand, not the histidine. So, that is cytochrome P450. Here we are discussing about the hemoglobin and myoglobin cases. This is histidine axial chain. As you can see, the high spin ferrous, that means Fe2 plus D7 iron system, high spin would mean T2G4 and Eg2, right. So, iron 2 plus means D6 electron system, sorry, and D6 electron system would be this T2G4 and Eg2 system, fine. Now, let us look at the low spin ferric. Of course, this is a iron 3 plus, that means it is a D5 electronic system. Since it is low spin, it is going to be T2G5. This is a superoxo. How do you know it is superoxo? Very simply, if you want, you can record UV visible spectra, which is characteristics of it, and you can also record resonance Raman, which is kind of definitive proof that it is superoxo species. You have seen for myoglobin cases it would be 1105 wave number for the oxygen stretch in resonance Raman. That means that it is without doubt this is the iron 3 superoxo species, right. That is fantastic, that is a superoxo species right over there, and this oxidation state change as well as spin state change you have seen very clearly. Okay. Now, this phenomenon you can follow in the enzyme in the form of, let us say, crystal structure. This is a nice crystal structure showing that iron 2 plus is outside the plane, histidine is bound. Once again, if it was cytochrome P450, here you would have cysteine bound with it, right. There is a there is many protein residue or this backbone from the amino acid backbone of the protein residue which is coming into the picture in the distal site. All these are appended towards this active site, giving rise to a great feeling for this oxygen binding. Okay, once the oxygen is binding with iron, of course at the first step there will be oxygen binding without any electron transfer, but immediately after that, immediately after oxygen binding, one electron from the iron center transferred to the oxygen to make it iron 3 plus superoxo. You start with iron 2 plus, you went to iron 3 plus superoxide species. This species is also affected by this by this protein side backbone or protein side chain, which overall helps in giving the geometry it is having, that is the bend geometry, and this is particularly why we see that the role of these histidine, phenylalanine and leucines are quite crucial for the oxygen binding. Okay. Now we also understand that this histidine will move in as soon as this iron center moves in the cavity, this histidine also moves inside this. This pull or this trigger will cause a trigger for the other iron center, other 3 iron center that is present in case of hemoglobin, to make them activate, to make them ready for the oxygen binding. So, one oxygen binding at the one of the iron center helps binding other iron with the oxygen center. So, this movement from this outside plane to inside plane, this overall upward movement for the histidine is quite important. As you have seen for in case of cytochrome P450, here it would be cysteine. Now this cysteine thiolate will help you overall in breaking the oxygen bond in case of that hydroperoxo OOH that is being formed, and then overall this iron oxo species subsequently after oxygen bond cleavage, whenever it is happening, that is in cytochrome P450, this iron 4 oxo or this high valent iron oxo species that can be generated in cytochrome P450, it will be stabilized, or it will be really easy for cytochrome P450 to have this cysteine which can stabilize such an intermediate. Okay. So, once again there are similarities between hemoglobin and cytochrome P450. Cytochrome P450 not only activates the oxygen, it actually also activates the substrate to do the chemistry. In case of hemoglobin and myoglobin cases, it is purely oxygen binding, right. You do not see any other reaction happening at the hemoglobin and myoglobin, and that is partly because, and of course partly because of the presence of these protein side chain and absence of any substrate and the substrate binding pocket. Has there been a substrate binding pocket and a substrate available, then we perhaps will not be living here, because these are the reason why we inhale oxygen and how we take up those oxygen and deliver at different part of the body. If this oxygen was involved into activity such as substrate hydroxylation chemistry, we will not have been getting this oxygen at different part of our body, which is essential for surviving different cells. So, therefore, this whole system, perhaps our whole system, biological system perhaps would have collapsed. So, as you see, nature has designed everything perfectly, that in this case it puts or it engages a histidine as opposed to the cysteine, and more importantly substrate binding pocket and non availability of substrate makes it perfect for hemoglobin iron center, protoporphyrin 9 center to act as just oxygen transport agent or center. It is not really participating in anything else. Its role is to reversibly bind. So, whenever it is required, it can bind and it can release oxygen. So, if this is the porphyrin center, oxygen can come in and binds with it. Of course, there is a superoxo formation after electron transfer, but wherever it is required it can release the oxygen. So, it is almost keeping the oxygen, watching the oxygen, but it does not engage oxygen too much into the reactivity. It is not like it cannot, it is capable of doing it, but overall architecture is such that it is just participating in oxygen binding and removal. This reversibility is so good that you do not see any loss of activity in these cases. If you want to do the same chemistry in synthetic setup, it is not that very easy. We have discussed that, we will briefly mention that again. So, the problem that happens with the synthetic chemistry is, well, the moment one iron center is bound with one oxygen, another iron center is also approaching it to form the iron 3 peroxo iron 3 species. So, it would be in between, as we have discussed earlier, it will cause problem. Let me briefly mention once again, and that is you will end up seeing. So, the moment you have a iron 2 porphyrin system, let us say P, it reacts with oxygen, okay, to give you, let us say this is leveled oxygen, if you are leveling, to give you iron 3 superoxo species. That is the first form species. This is the superoxo species radical cation. So, it breaks to give you iron 3 superoxo species. Subsequently, from there another porphyrin iron 2 species comes in and it gives 1 electron to it, and essentially it gives porphyrin iron 3 oxygen and iron 3 porphyrin species, right. So, this species is now then can further react. So, in case of enzyme it stabilizes over here, there is no problem, because there is not the second iron center or second porphyrin center is not really available, because enzymes are protecting every site very perfectly. But in synthetic studies, when you are trying to do this chemistry in laboratory, you can get this chemistry, but you can of course get this chemistry, but this is not limited, or this is not staying right over there. It can further react with another equivalent of porphyrin iron 3 which is present into the solution and can give the peroxo species. So, this is the iron 3 oxygen and iron 3 peroxo species. This species of course also reactive, further it can go on and react, and finally it will perhaps stop reacting at this point when you have this iron 3 oxo or mu oxo porphyrin iron 3. This is relatively stable compound, so it is goes there. You can see that this is kind of a thermodynamic sink, right. This is not what you want. You want this to be reversible and it stays over there. That is what is happening. All this reversible chemistry is happening in enzyme. The first in enzyme case, this is where it gets stabilized, but in synthetic chemistry setup you end up getting these side reaction which causes the majority of the problem, and therefore mimicking this chemistry in synthetic setup is extremely difficult, because we want to mimic just the reversible binding. We do not want to get any reactivity out of it. We do not want to react it with any other substrate or anything, because we want to see the hemoglobin chemistry, which is the reversible oxygen binding, right. In synthetic setup, most of the studies that has been done so far fails to mimic this reversible oxygen binding completely, because it not only does this chemistry, but it overreacts, right. This is the problem. Of course, it is possible to mimic, but it overreacts and therefore it leads to the side product formation, right. So, let us go back. So, to prevent this overreaction or even the auto oxidation of iron 2 plus to iron 3 plus, which is again another problem, because this iron 2 plus stabilizing them in iron 2 plus is very difficult, because it is very sensitive, it is air sensitive and moisture sensitive. All these species need to be recorded or need to be stabilized, stored in glove box, right. This is very sensitive chemistry. Now to prevent that second iron center to come close to the first iron center where a superoxide species is forming, it has been successfully designed to have this picket fence porphyrin, which is essentially helping you in getting the mononuclear. So, mononuclear iron superoxide species, these oxygen binding are reversible in nature. In this case you see that axial ligand is also there in the form of imidazole, which is similar to what we see in histidine, right. So, this picket fence porphyrin can mimic the reversible oxygen binding of the hemoglobin. Also there is this capped porphyrin, as you see it is a really nice drawing and really nice molecule where as if there is an umbrella in front of the iron site which is protecting from another molecule of these to come very close to each other. So, this proximal site is blocked by the histidine and the distal site is open where oxygen binding can happen, and oxygen binding, once it happens, this intermediate, which is very reactive intermediate, despite having high reactivity of this iron 3 superoxo, it still does not really react with another equivalent of this molecule due to the steric hindrance or the bucket shape of these species, right. So, this overall umbrella thing or umbrella design helps in stabilizing the intermediate perfectly. Now that is what we have seen. So, in hemoglobin and myoglobin cases, you know that there is no substrate activation, it is purely oxygen binding, right. It is a reversible oxygen binding. After much effort, synthetic chemist can mimic those features of hemoglobin and myoglobin. By mimicking or by copying the activity of the hemoglobin myoglobin, it gives an opportunity to better understand what happens in hemoglobin and myoglobin. Even at a molecular level, things can be done which were not otherwise possible. The problem of the dimerization or the dinuclear iron species formation can be prevented somehow by putting this big picket fence or capped porphyrin design. Let us look at another enzyme, that is hemerythrin. Before that, just to mention once again, this is 1105 wave number for oxygenated myoglobin. This is matching quite well for the superoxo species. Okay. If you have a crystal structure, that can also give the oxygen stretch in this region, which is quite exciting in any case. Okay. Let us look at the hemerythrin. As you have seen, hemerythrin is a di-iron center. Okay. These are non-hem center. So, hemoglobin is found in some, like let us say in higher species such as us, in all other mammals, in majority of the species are having hemoglobin, but then there is these marine invertebrates and some other species where you do not have the hemoglobin cases, where you do not have the hemoglobin iron oxygen binding center, and this is where these iron 2 di-iron center will be coming into picture. These are not porphyrin ring, or these are having these histidine, simple histidine ligation. These histidine ligation are quite phenomenal, quite important, because it provides the opportunity for these species to carry oxygen, invertebrates to carry oxygen. Before oxygen binding, it was a colorless species. Upon oxygen binding, so colorless species is this one, upon oxygen binding it becomes red. So, this is a red color species. This oxygen binding, just like hemoglobin and myoglobin, is reversible in nature. That means it is pretty easily can go forward and backward, and therefore the oxygen transport and release can be easily possible, right. If you are looking at this species, so this species will form a peroxo species. Let me draw it very quickly. So, what you will see here is you are having a di-iron center, right. I am not drawing bridging too much. So, it is a di-iron center, you are reacting with oxygen, let us say level the oxygen, you get a di-iron. Of course, I will draw stepwise, not necessarily these intermediate you form and stabilize very easily. You, of course, it is forming, but you cannot stabilize. So, in the first step it is a iron 2 iron 3 species, while only one of the iron site will bind this oxygen, because the other side, as you have seen, is having 3 histidine, nitrogen, 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 these are histidine nitrogen. The other side is having only 2 nitrogen, histidine, histidine, right. So, of course, there is bridging, I am not trying to draw those, there is a double bridging anyway. So, these are over there, oxygen, oxygen, let us not try to draw the whole system. So, this is unsymmetrical iron center, as you have seen over here. You have a iron 2 plus center with 3 histidine, on this side it is 2 histidine, right, and then you have the oxygen molecule in there, right. This oxygen molecule binds with it, one of them, the one which is unsymmetrical or which is having less ligand, this is 3 histidine ligand, this is having 2 histidine ligand. So, this is the site where oxygen binds, and upon binding the oxygen, it can then through the bridge, since it is through the bridge, it can. So, of course, this intermediate you cannot see such intermediate. This is iron 3 superoxo intermediate, perhaps it is going to be extremely difficult to stabilize. So, immediately another electron transfer happens to it to give you a peroxo intermediate. So, as you have seen, this is going to be 2 minus, the whole thing is going to be 2 minus. So, this was 1 minus superoxo, this is a superoxo, this is a peroxo. Of course, just remember that it is not really possible to see such intermediate, just I am drawing stepwise for your clarity or for you to understand very simply. So, both the iron 2 plus center give 1 electron at a time to give the iron 3 peroxo species. This iron 3 peroxo species subsequently can be protonated, as you have seen over there. So, this is going to be a completely proton transfer. So, proton coupled electron transfer, perhaps in this step this is going to be at a step, not even this intermediate you will be seeing. So, overall you will be seeing the formation of iron 3 oxo iron 3 hydroperoxo intermediate, right. So, this is your oxygen that is coming on, this is your oxygen from the oxygen atom, and there is a hydrogen bonding, and rest of the things are still there, right, still there. Okay, so I do not think it is fair to draw the intermediate, because not such intermediate existence is questionable, both the intermediate. So, iron 2 you start with, immediately you get iron 3 hydroperoxo. So, this is a proton transfer. The way I have shown you is electron transfer first and then proton transfer. Perhaps that is not going to happen, it is going to be proton coupled electron transfer, directly it is forming. So, one electron from this side, another electron from that side, it makes it iron 3 peroxo, and then protonation. So, immediately all of them are happening. So, it could be one electron transfer and one proton coupled electron transfer, PCET, that is what is happening. Stepwise drawing this mechanism is not perhaps fair, because no such intermediate exists, and we cannot say for sure what exactly happens in a stepwise fashion. But as you have seen over here, you can see that this is hydroxo intermediate, and upon oxygen binding it forms these from iron 2 a iron 3 hydroperoxo intermediate, which is hydrogen bonded through this mu oxo species, right. If you try to record the resonance Raman of this oxygen stretch, you find that it is at 844 wave number, which is matching perfectly for the peroxo species. So, in the first case of hemoglobin myoglobin, you see that it is a iron 3 superoxo species, it is formed upon oxygen binding, it does not go anywhere after that. But in case of hemerythrin, it is one more electron reduced species and protonation, that is iron hydroperoxo species. It is a di-iron species and it is a bridge species, that is quite phenomenal. I think pretty exciting intermediate, and these species are spectroscopically characterized, and you can see the spectral behavior right over here, right. So, let us move on and try to see what we can get in case of the synthetic modeling studies. As you have seen in the synthetic modeling studies, it would require the 3 histidine on one side or 3 nitrogen binding on one side, another side would have 2 nitrogen binding. Synthetic chemists has been very efficient in mimicking this, and it was possible to mimic almost exactly the spectral feature. So, synthetic chemist has been extremely successful in mimicking this activity, and we see that it is possible, it is actually possible to get the exact 3 histidine or 3 nitrogen binding on one iron site, another iron site will have the 2 nitrogen binding and the hydroperoxo species formation, oxygen stretching, and all the other spectroscopic features, UV visible, Moss-Boyer spectra are exactly similar to what is found in the enzyme. That is fantastic, and these are completely reversible oxygen binding in the enzyme, that is fine. So, you have seen the difference between hemoglobin and hemerythrin. Let us quickly look at the hemocyanin. As you have remembered, perhaps it is a 2 copper center as opposed to 2 iron center in hemerythrin. This is found in arthropods and mollusks. So, for example, lobster, crayfish, arachnids, all are having this sort of copper center or di-copper center for oxygen binding. 3 histidine is bound with 1 copper, another copper is having another 3 histidine, and the oxygen is getting reduced by 2 electron, 1 electron each from each of these copper to form the iron peroxo species. You can see the distance between these 2 copper center was 4.6 angstrom, it is reduced to 3.6 angstrom upon the oxygen binding. So, these are trigonal planar copper 1 center, and these are super sensitive. Okay. This can react with oxygen while almost immediately, right. These are completely reversible oxygen binding, and upon oxygen binding it forms the peroxo, that means 2 electron reduced species, which has a characteristic peak of oxygen stretch 750 wave number, which once again just like what you have seen in hemerythrin are peroxo, but it is a different type of peroxo. It is a side-on peroxo. In the hemerythrin you have seen a hydroperoxo, and in almost an end-on version, right. So, therefore, these species are all different, both hemoglobin, hemerythrin are different compared to hemocyanin, but one thing puts them in common box, and that is they are capable of transporting oxygen. They do not utilize oxygen for any other activity other than transporting, right. So, that makes them very interesting. This species is colorless in nature, this species is blue in nature. In all these cases you have seen hemoglobin bead, hemoglobin, hemerythrin or hemocyanin, all these cases oxygenated species are really bright color, right. You have seen red and blue, hemoglobin, hemerythrin and hemocyanin. That makes it quite exciting. As you know, there exist a number of synthetic mimic that exactly kind of nowadays mimic what is happening in hemocyanin. The efforts for mimicking with a tetradentate ligand is this one, we will discuss, we have discussed this before. With the bidentate mimic is this one, but the one which is found in hemocyanin is exactly this one, which is found with this tridentate ligand backbone, right, which is fantastic, and it matches exactly the spectroscopic features, also both UV visible and resonance Raman. So, therefore, let me summarize by telling you that, as you have seen, hemoglobin myoglobin, of course, hemoglobin, myoglobin, hemerythrin and hemocyanin, these are all great enzymes and they are all capable of binding oxygen in a reversible format, and they are not interested in anything else. Nature has designed these in such a way so that there is no substrate available. You know what will happen if a organic substrate is available in front of this, you have seen it, okay. We will summarize that as well in another class, but if there is a substrate available in front of this, it will end up reacting, because all of these intermediate in hemoglobin, myoglobin, hemocyanin, hemerythrin, all of them are reactive intermediate. Since there is the design or architecture does not allow to have any organic substrate present in front of them, therefore they are sitting pretty and idle, they are not going to do any chemistry, they will be as if their hands are tied and they are very happy to just transport the oxygen and deliver it, okay. So that is all for today, but as you know, this chemistry takes quite an interesting turn when you have cytochrome P450 or tyrosinase, for example for hemocyanin. You see this chemistry becomes much more beautiful, much more exciting in terms of substrate oxygenation chemistry or the synthetic chemistry. We will come back to those in summarizing those in the next class. Thank you very much, keep studying.